week 5, now we are looking at null space of a matrix. So quickly, before looking at what's the null space of a matrix, so suppose let's say you have an m by n matrix, okay, and I am talking about let's say range of A or the corresponding transformation range of T. Should I look at the rows or columns of A?
Columns.
For what, ma'am?
For range. Okay. For range, you should look at the columns. So range is your column space. Though the dimensions of row space and column space are same, but range is exactly the column space of A. Remember that. Okay. And remember, range is always a subspace of the codomain, and null space is always a subspace of, suppose you are considering, let's say, so if it is an m by n, then the corresponding transformation is from Rn to Rm, right? So always range is a subspace of codomain, and null space is a subspace of
Domain.
domain. Okay. So null space is a subspace of domain. So this you should have in mind. Okay. Good. So what is the null space? You know that the set of all x in R and such that x is equal to 0. Right? The solution of the homogeneous system. Right? And is this always non-empty?
Yes.
Because we always have the 0 vector in this. So this is a non-empty space. In fact, it is a subspace. So always 0 is there in this. Right? And the dimension of this particular subspace is called the nullity of the matrix. Right? Okay, so here is a quick problem. Consider the system of linear equation Ax is equal to 0. So this is your matrix A. Okay, so choose the correct statement from the following options. So here from this matrix, what are the dependent and independent variables? So for
When x and
identifying
x3 are
the,
dependent.
2 is independent.
okay, so we have to look at the pivot elements. So first of all, is the matrix already in RREF form?
Oh, sorry.
Yes, ma'am.
Yes, ma'am.
No.
Yes.
Second row.
No, ma'am.
Second row
Yes,
should
ma'am.
be.
Second row should be third row.
Second row should be the last.
Yeah, so we can first shift it to RREF form. So if we are bringing it to RREF form, then this is your RREF form. Okay. Now in this RREF form, now you look at what are the pivot elements. What are the pivot elements? This is a pivot element, and this is the pivot element.
First and
Yeah.
third.
So you have pivot element in the first column and third column, right? So 1 and 3 contains pivot element. So if it contains pivot, then what can you say about x1 and x3? x1 and x3 are
Dependent variables.
Dependent.
1 and x3 are dependent variables. So x2 is the independent variable. Right? Okay. So what should be the rank here?
2.
2.
Rank is 2 and nullity is
1.
1. Okay, fine. So here you see that here you have x1, x2, x3 all are dependent, which is incorrect. x2 is the only dependent variable, which is again incorrect. x1 and x3 are dependent variables and x2 is the only independent variable. So this is the correct option.
Correct option.
Yeah. So the other options are incorrect. What is the null space and nullity of A? What's the null space of this matrix? How do you calculate the null space of this matrix?
Put the matrix as equals to 0.
Yeah. So
101.
So A is, yeah. So what are they? So this is your matrix. So it's very easy to identify in this case. Can you quickly say what are the what elements in the null space? What
101.
one
x1 equals 0 and x3
uh,
equals 0.
x1 equal to 0 and x3 equal to 0 exactly, right? So if you have ax is equal to 0, then that will give you like 1 0 0 0 0. Please mute yourself. There is too much noise. Yeah. So x1, x2, x3, this is 0, 0, 0. Now this will tell you that x1 is 0 and x3 is 0. So x1 is 0 and x3 is 0. So x2 is your independent variable, right? So you have null space of A is at a fall 0 comma t comma 0, t varying in R, or you can write it as span of 0, 1, 0. Okay, so you see that this forms a basis for null space of A. Okay, fine. All right. So from this, obviously, you see that there is one element in the basis of the null space, so nullity is 1. Okay, so you can see it in this way as well. All right.
Ma'am,
Now,
nullity is dimension of null space, right?
yes. Okay, so you can see that this space is spanned by only one vector. So the basis, this is a basis for this space. So and hence you say that nullity is 1. Okay. All right.
Ma'am, can you explain null space again?
Null space is just a set of all x such that ax is equal to 0. This is a very simple case where I have solved ax is equal to 0. So you see that from this equation x1 and x3 are 0 and x2 is an independent variable. So I choose it as just some t where t is any real number. So now you know that this is nothing but span of 0, 1, 0, and the 0, 1, 0 is a basis for this null space. Hence nullity is the number of elements in the basis. So number of elements in basis is exactly 1. So nullity is 1. Clear? Yeah.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So here is the problem. Consider a system of linear equation defined as follows. So here, what is the size of? Suppose you are writing it as let's say a u equal to 0, where u is this vector x, y, z, w. So what is the size of this matrix A first of all?
4 by
3
3.
by
3 by 4.
3 by 4.
Right? It is a 3. So you see that. So if A is the coefficient matrix of the system of linear equation, then which of the following option is true? So obviously your null space is a subspace of R4, right? So how do we quickly find the null space of this? Either you find the RREF form, right? So usually we find the RREF form. How many of you remember finding the RREF form? So first of all, what is the matrix here? Let's quickly write what is the matrix.
1 1 minus 1 1. 2 1 3 minus 1. 3 2 0 2.
3220,
2 0,
right?
ma'am. 2
2
0.
0, yes.
Okay. So now this is your matrix A. So to find the RREF, so you need to follow certain steps. I'm going to straight away write the RREF because we don't have sufficient time to do all the steps. So the RREF form of this matrix, I'm directly writing. So it is 1, 0, 4, minus 2, 0, 1, minus 5, 3, 0, 0, 0, 0. Okay. So now where are the pivot elements? So this is a pivot and this is a pivot, right? So you see column 1 and column 2 are having the pivot elements. So it means what are the dependent and independent variables? So x1 and x2 are the dependent
Dependent.
Variables.
Dependent.
and x3 and x4 are the
Independent.
Independent.
okay. Now once we have the RREF, we can compute the nullity directly from this. So if you use this matrix to compute the nullity, so let's call this maybe A dash. So A dash u equal to 0 gives you what? X plus 4z minus 2w equal to 0, and then y minus 5z plus 3w is equal to 0. So now here, actually here, what is your x1, x2, x3, x4?
Ma'am, it is REF form or
Yeah,
RREF form?
RREF.
I think REF. Ma'am, okay, RREF. Okay, fine.
Yeah. So here, let's maybe write x, y, z, and w. Okay. Now you know that z and w are the independent variables, so you can choose them to be some t1 and t2. So let's say your z is some t1 and w is t2, right? So in that case, what is your x? Your x is 2t2 minus 4t1,
41.
and your y is
5T1 minus 3T2.
5t1 minus 3t2. Okay. So now can you write what's the null space?
-4, 5, 1, 0, and 2, -3, and 0, 1.
2t2 minus 4t1, 5t1 minus 3t2, comma t1, comma t2, very in R, right? So you know that you can write it as, so yeah, you can have it a span of maybe 2, 5, or not 2, -4, 5, 1, 0, and so on. But here, what is that we have? Based on that, we have to see. So maybe let's write it the other way around. That makes it better. I'll write t1 first and then t2 so that it's easier to do the splittings. So if you do the splittings, then what will you get? -4, comma 5, comma 1, comma 0 times of t1 plus -2, -3, 0, 1, t2, correct? So t1, t2 in R. Okay. So this is how you can write the null space of A, and you know that this will form a base. These two
There would
vectors will
be
form a base.
+2. I guess there would be +2 in the second vector.
Oh yeah. Thanks. All right. So now let's compare the options. So you have -4, 5, 1, 0. Yeah, this vector is correct. And then 2, -3, 0, 1. Yeah, this is also correct. Okay. And we have the same -4, 5, 1, 0 here. So this vector is correct. What about this vector? What about this vector?
Yeah, it is
Not
correct. It is just the second vector is multiplied by 2, I guess.
So this, it looks like, so let's call this maybe V1 and V2. So this looks like V1 minus V2. Is that correct? Yeah.
Yes, ma'am.
a linear
Yeah.
combination.
So you can say that this is also then linearly independent, and hence this will also form a basis, right? So can we say that this is also a spanning set for the null space of A?
Yes, ma'am.
Yeah.
Yes,
Okay.
ma'am.
Now here we are again having, so this is actually V1. So here in this case, we are having V2 here. What about this vector -3, 5, 1, 0? Is it there in the null space or not? So whether
No, ma'am.
you when you multiply with this, whether you are getting it as 0 or not. For example, -3 plus 5, it is 2, and then -1, it is just 1, not 0. So this does not belong to null of A. Correct? Do you see why this does not belong to null space? Just put it in the equations. You will see that you are not getting 0. Right?
We can do
So that's
the
why.
same first two options, right?
Sorry, what?
And we can also do the same thing for the first two options as well, right?
But in the first two option, the vectors were in the null space, so you were able to figure out. But here, this vector is not in the null space, so you are exactly the same thing you are trying here. So you are checking whether you are able to write it as a linear combination of these two. So we are checking that. So if it is not, we are see, either you have to check whether you are able to find T1 or T2, or you have to see whether it is first of all there in this null space or not. That's all.
Okay.
Ma'am, can you repeat this method of finding out?
No, ma'am. One doubt, ma'am. Without solving this fully, finally you said no. We can substitute in the equations.
Exactly. You can do that from the beginning itself. Yes.
Yeah. That's the
Yes,
question.
ma'am. That's what I asked, ma'am.
Yeah, you can do it.
Ma'am, can you
Okay.
repeat this method like of putting like
See, whatever vector you are having here. So here the vector is -3, 5, 1, 0, right? So this -3, 5, 1, 0. First of all, is it there in the null space or not? You have to check. So here you put -3 plus 5 minus 1 plus 0. So what is the answer you are getting? This is not 0. So this means this does not belong to null of 8. Is that fine?
ma'am, the vectors which are in the null space will satisfy all the three equations.
Yes, it should satisfy all the three equations. If it does not satisfy any one also, then it cannot be there in the null space, right?
Okay, yes.
Yeah. So you can verify in the same way. What do you think about the last two options? Can you quickly verify and tell me whether they belong to the null space or not?
Ma'am, if it satisfies suppose all the three equations, then both the
It is
vectors.
there in the null space. Yes, it is there in the null space.
And if one of the vectors does not satisfy out of two vectors, then it is not a.
Yeah, correct. So for example,
No,
minus
ma'am.
4.
Option 4 is not in null space.
Yeah. So you see that this is also not in null space of A. So you can say that only option 1 and 2 are correct and 3 and 4 are incorrect. Is it fine? Yeah?
Ma'am. Yes, ma'am.
Okay, good. All right. So we know that we can use the rank nullity theorem in many cases, right? For example, even in the first example we saw, we know that, right? Immediately looking at this matrix, what is the rank we know. But this is a mistake which many people do. See, everyone listen carefully. The number of non-zero rows in the RREF form is the rank of the matrix. That is true. But is the number of zero rows equal to the nullity?
No, ma'am.
No, ma'am.
No, ma'am.
Please don't make
No,
this
ma'am.
mistake. Yes, it is not the nullity always. Sometimes, for example, in the square matrix case, yes, it is coinciding. But for example, you take this case. So what is the nullity in this case? The nullity is
2.
2.
right.
2.
But how many number of zero rows are there?
Only one.
One.
1.
1.
1.
Look at the number of dependent and independent variables. That will make sense. Okay, so don't make this mistake of counting the number of zero rows. Never count the zero rows. Only count the non-zero rows and then go to rank nullity theorem. Okay, fine. So yeah, this looks like the same set of equation we were having in the previous set. So
So
we
n,
have
n is the order. Means rank of A plus nullity of A is equal to n. So n is order.
and it's the number of columns.
Got it.
So looking at columns will not cause that error right now. Instead
Sorry,
of,
what?
I mean, instead of non-zero rows, we can look at non-zero columns and zero columns. Right?
Yeah, that will make sense. Yeah. Okay, but non-zero rows, but what does it, see, you have to look at the columns containing pivot and not containing pivot. It does not make sense to consider zero and non-zero columns. It does not make sense. Okay, columns containing pivot and not containing pivot. That's all in RREF.
Ma'am, but as I was doing questions, I see a pattern regarding the variables and the columns. I guess columns are more like in correspondence with the variables. Like
Okay.
the given number of like if there are non-pivot elements having non-pivot columns, then it is more corresponding with the independent columns or independent variables and non-independent variables.
Yeah, this is the definition of dependent and independent variables. That is how you see it, right?
Yes, ma'am. So,
Okay. Yeah.
using seeing the columns, the seeing the pivots through the columns would be much more beneficial, in
Yes,
my opinion.
exactly. Exactly. The dependent variables contribute to the rank and independent variable contributes to the nullity.
Ma'am, suppose if you want to check if three vectors form the basis of null space,
Mm.
and if all the three satisfy the equations given,
Mm.
then they necessarily be basis, we can say.
No, you also have to look at linear independence.
Because one could be linear combination of other two, no?
Yeah, you also have to look at linear independence. So in two vector case, it is very easy because you just have to check one is a multiple of the other or not. But if it is more than two vectors, then you also have to be careful about linear independence part.
Yes, ma'am.
Okay.
Thank you.
Okay. Okay. So for first two options we already have verified. Okay. So next, let's move to the next three. If A 3 by 2 is a non-zero matrix, then the nullity of why it is 3 by 2. Is it asking for a general matrix or the statement is not correct? If A is a non-zero matrix, then the nullity of, I guess they are asking a general statement here, I guess, or some questions are
Ma'am,
kind of.
ma'am, rank will be maximum 2, no?
Oh, I guess this is kind of my mistake. When I'm making this PDF, I kind of put this question here by mistake, I guess. So here, this is not the question here actually. So let me write the question here. So the question here is find the correct options. So option 1 is if A 2 by 3 is a non-zero matrix, then nullity of A is less equal to 2. So this is the first option, and then you have 2, 3, and 4. Okay, so ignore this part here. Okay, by mistake I called the previous.
Ma'am, option 2, we cannot have rank 0 because it is a non-zero matrix.
Yes.
Can't
So
have nullity.
minimum rank is 1, so and total number
So
of
nullity will be 0.
so nullity will be maximum 1, ma'am.
Okay, let's check that. Okay. Okay. So what is the argument we are having here? So since A is a non-zero matrix, A is non-zero. So this means that rank is at least 1. Right? So what do we know also that rank of A plus nullity of A, can you say is equal to what for a 2 by 3 matrix? It's 3 by 2 or 2 by 3?
2.
3
For
by
a
2. 3 by 2.
Option 2.
in this case it is 2 by 3.
Number of
So
columns.
let's first look at option 1. So in this case it is a 2 by 3 matrix. So here it is equal to
3.
3.
right. So now we know that the rank is at least 1. Okay, and what is the maximum possible rank?
3.
3.
3.
No,
2.
And maximum possible rank is 1.
no.
Maximum 2.
Saying all possible 1, 2, 3s, huh?
2.
What is the correct
And
answer?
maximum can be 2, no?
Yes, because rank of A
2.
is
Minimum
whether, yeah,
of
Minimum of
M
row
comma
and column.
M.
for an n by n matrix, it is less than or equal to minimum of m comma n. So here the minimum is 2. So you know that rank is 2, less equal to 2. So either it can be 1 or 2. So these are the only possible options for this matrix. So here A can be 1, rank can be 1 or 2. So if rank is 1, what is the possible value for the nullity?
2.
And if rank is 2, then the possible value
1.
1.
So what is it? We can see that nullity, here the question is nullity is less equal to 2, which is correct.
Correct.
Yeah. So we can agree that nullity is less than or equal to 2. That is correct. Okay. Now what is option 2 saying? Option 2 is about a 3 cross 2 matrix. So option 2, we are having a 3 cross 2 matrix. So for 3 cross 2 matrix, again it is non-zero. So we have the same condition. Again 3 cross 2. So again we have this also. So you have 1 less equal to rank of A less equal to 2. So this we have anyway because of the same conditions, right? But what about the rank nullity theorem? Rank plus nullity is equal to what in this case?
2.
2, right? So in that case, so suppose if you have the rank is 1, then the nullity is 1. And if the rank is 2, then the nullity is
0.
0.
0,
Zero.
right? In that case, here if a 3 by 2 matrix is a non-zero matrix, then the nullity of the matrix is less equal to 1. Is that correct? Nullity is less
Yes.
equal to 1. Yeah, it's correct, right? Okay. Now, option 3. Let A and B be two square matrices of order 3. If nullity of matrix AB is 0, then the nullity of the matrix A is also 0. What do you think?
No.
Okay. So, first of all, let's analyze the situation. So, AB is a square matrix because A and B both are square matrices. AB is also square matrix. What is the order of this matrix? A and B are square matrices of order 3. So AB should be a
N,
3 cross
N by N.
3 cross 3 matrix, right? And it is given that nullity of AB is 0. So it is given nullity of AB is 0. If nullity of AB is 0, what can you say about rank of AB?
Rank
Full
should
rank.
be
3.
Rank is 3.
3.
3. If rank is 3, what can you say about the determinant of AB?
non-zero.
Non-zero.
If this determinant is non-zero, what can you say about the determinant of A?
Non-zero.
Non-zero.
So what can you say about nullity of A now?
0.
Right? Actually, from here directly you can come to this conclusion. Just maybe I thought first I will do this and here you know what's happening. Right? So what is the condition here we are looking at? So if you have an n by please move. Okay. So if you are having an n by n matrix, okay, and let's say the following conditions are true, right? So rank, let me write it properly. So you have rank of A equal to n only if nullity of A is equal to 0, if and only if determinant of A is non-zero, right? All these conditions are equivalent, right? So keep this in mind. Okay, in this case, what can you say about the range? Range of A?
3.
N.
Rn, right? And null space of A.
0.
0.
Okay. So because of this relationship, we are able to conclude that here nullity is 0. Okay.
Excuse me, ma'am.
Ma'am,
Yes,
Ma'am, how you decide nullity of AB equals 0? AB.
it is given. Nullity of AB is 0 is given.
Okay, I didn't see the question. Okay.
ma'am, how this range and null space, how they are coming? I didn't get it actually.
Okay. So if rank is n, so it means the dimension of the range space is n, right? So what is the subspace of
Ma'am,
Rn which has dimension n?
ma'am, why range space has dimension n if rank is n?
That is the definition, right? This is the dimension of range of A, right?
Because we will have n number of variables, right?
Yeah. So here you see the dimension of range of A is n, and that range is a subspace of Rn. So which subspace can have like n basis vectors for Rn. It can be just Rn, cannot be anything else apart from that, right?
Yeah,
Ma'am,
yeah. Okay.
Yeah, yeah, go ahead.
if we were if we were given that rank of A is something and rank of B is something, then rank of AB is minimum of uh, rank of A and rank of B. Is there any theorem regarding this?
Yeah, so you have rank of AB less than or equal to minimum of rank of A, rank of B.
Yes, ma'am. Can you explain this part?
Which part?
If we were given rank of A and rank of B, then what can we say about the rank of A and A into B?
So exactly the same condition like here. So if you want that, so it's like this. So rank of AB is less equal to minimum of rank of A, comma rank of B. Okay. Okay. Fine. All right. So I guess okay. So let me just ask a quick question. See, if I am able to go in my flow, then I will be able to complete the questions I have planned. But if you have questions in between, it's okay. It's good to ask questions in between. But if I'm going to like keep on adding so much of details in between, then I might not be able to cover what I intended to. So don't be disappointed if I did not cover all the slides I prepared. So there are some problems where I have prepared. So if I am not able to complete it everything, then maybe I'll tell the TAs to complete. Okay. Or maybe I'll just send the entire PDF to you, and whatever problems you have questions, that maybe you can discuss in the TA session. Okay. Fine. So let's continue here. So what do you think about option 4? Think in the same context. So think in the same context as option 3. So what can you say about option 4?
True.
True, right? Because of exact same reasons, you know that option 4 is also true, right? Fine. Okay. Okay. So here you have A and B are two square matrices of order 2. So both are 2 by 2 matrices. Now, which of the following options are true? What do you think about option 1?
Wrong.
False.
No, false.
Okay, so you are saying everything is false. If everything is false, how do you know that?
Mm,
Since the order remains the same, so in the first and second, the order remains the same, 2 cross 2.
So in
So
this case, you just have to establish some counter examples. That is the usual way we do, right?
yeah,
Yeah. For example, see, when usually for making counter examples, we usually take matrices with ones and zeros because that is where we get easier examples. So suppose you are taking A is this and B is this. What is AB?
Square matrix of order 2.
The same matrix actually, right?
just one
So
order
what's nullity of A?
1.
1.
What's nullity of B?
One.
1.
One.
One.
In fact, all are same matrices, so you know that everything has nullity. So in this, from this, what about the first one? Can we say that option 1 is incorrect from this?
yes, ma'am.
Yes,
Yeah.
ma'am.
Yes, ma'am.
So we can see that this is incorrect. What about option 2? Can we use this? No, we cannot use this. What about option 3?
We can take a diagonal matrix.
No.
1,
So A minus, what
1.
is nullity of A minus B?
Zero.
0.
Zero.
Come on. Think carefully.
2. 2. Sorry, 2.
No,
2.
two.
2.
Two.
Yeah, so nullity of A minus B is 2, right? Because A minus B is the zero matrix.
Ma'am, why can't we use option 2? Because it is following the condition nullity AB.
So this particular example, I cannot use it for option 2. That's what I said. I did not say option 2 is correct or not. I just said that this example cannot be used
And
for.
option 2 is also wrong because if one of the matrices gets nullity equal to, then multiplying it, then it will
Yeah,
change to
I have
1.
discussed about option 2, but I just said that this option is not suitable for option 2. Okay, good. So nullity of A minus B is equal to 2. Now, what is nullity of, please mute, please mute. If you're not talking, please mute. Yeah. What is nullity of A minus nullity of B in this case? It's 0. So here in this case, you will get for option 3, you're getting RHS is 2 and LHS is 0. So this is also incorrect. So for option 1 from here, the RHS, maybe I wrote the LHS and RHS. So your LHS is actually 2 and RHS is 0. So option 1, what is your RHS? Your RHS is 2. And what is your LHS? Nullity of AB is 1. So this is incorrect. What about option 4? Can we use this? Okay, so yeah, so you know that rank of A is 1, rank of B is also 1, rank of AB is also 1. Right? So rank of A plus B, what is A plus B? So rank of A plus B is also
1.
So for option 4, you can see that the RHS is actually 2 and your LHS is 1. So this will not work. Okay. And what about option 2? Again, we need some examples. So maybe let me consider a matrix. Okay, maybe I.
Ma'am, if we take
Identity matrix,
identity
identity
matrix,
matrix of order 2.
Okay,
So
let's
this
try identity matrix.
0.
So nullity is 0. Okay. What about AC? AC is equal to A, right? So here in this case, nullity of C, but are we getting AC is equal to A? So nullity of AC, this side LHS is, so in this case, what is your LHS for option 2? Nullity of AC is
0.
1.
0. 0.
0.
No. What is A
It
into
is
C?
1.
A, right?
Nullity of A is coming as 0 always.
This is your.
Rank is
1 initially 1.
Okay, maybe I'll call this some B dash, then you will have an understanding. B dash. Okay. So nullity of your A B dash is nullity of A, because A B dash is simply A, right? Because you are multiplying with identity matrix. Is nullity of A. So you will get nullity of A is 1. So your LHS is 1. And your RHS, since nullity of this B dash is 0, RHS is 0. So you anyway see that this option is incorrect. Okay, fine. So none of the options are correct.
Ma'am, without going through these steps, we can directly infer from that all options are correct or wrong.
It is very difficult. See, you have to use rank-nullity theorem, rank of AB less equal to minimum of all these things you have to use, but still that is not enough in some places. So it's sometimes really necessary that you need to construct some counter examples.
Ma'am, AB, we are finding nullity of AB means AB is a matrix of order 3 by 8. We are taking it 2 by 2. It cannot be exceed 2 by 2.
Yes.
So you cannot multiply it. Nullity of AB cannot be equal to nullity of A into nullity of B in every case.
Why? Why it is possible that some specific A and for some specific A and B it can be same, right? What's wrong?
They are giving for a generalized case. A and B are square matrix of order 2.
Yeah. They are giving for a generalized case, and for general case it is true or not. That is what we checked. We saw that it is not true. Yes. So what's your question here?
A and B are matrices. Then AB is again a matrix of order same
Yeah.
dimension.
Yeah.
Then nullity of A, we can find out nullity of A is mainly we can assume values and put it nullity of, if nullity of A is 2, then B is then nullity of AB is again 0. It make 2. In the case of nullity of A is 2, in that case nullity of B becomes 0. So
Okay.
nullity of A into nullity of B becomes 0.
Okay.
In that case,
So
we can argue.
what can you argue? Sorry, you are saying that nullity of A is 0 or A itself is 0?
Nullity of, suppose nullity of AB is 0.
Nullity of AB is 0. Okay.
I am arguing that AB is A and B are matrices, and then we get AB as a matrix.
Yes.
2 by 2. Right? The greatest,
Yes.
the highest nullity is 2 or lowest is 0.
Yes.
Then assume nullity of A is 1, nullity of B is again it can be 1. Then then 2 cannot be equal to 1 into 1.
Okay, so how do you know that nullity of AB is 2? For that only we need some concrete matrices. Okay,
Actually, I
that's what
think she's talking about all the combinations, as this is an order 2 matrix. She's talking about all the combinations of the nullity. Like at a time, there will be nullity of combination 0, 1, 1, 0, 2, 2, like that.
is that what you're talking? But why you need to look at all the possible combinations? I don't understand.
It is the same as taking counter example.
Okay, see, if you are giving counter example, then I don't know what you said. I did not make sense completely to me. See, counter examples can be given in several ways, or counter arguments can be given instead of counter examples, but it should just make sense. That's all. There need not be one specific solution, particularly for math. You know that any problem has infinitely many ways of giving solutions. So if you are able to come up with the proper logic for this, yeah, you can give your answer in some other way as well. Okay. Sorry, I did not get what you were trying to say. Maybe if you want, you can try putting a discourse forum of what you are thinking and see whether your thinking is correct or not. Sorry, here it's taking too much time now. Okay, let's move on.
Okay, sorry.
Excuse me, ma'am.
Yeah.
These four options, it's true only for order 2 matrix, or
they are not true for any matrices.
not true. Only
Yeah.
for order 2 only. This is okay.
Not
Okay.
only for order 2, for any matrix, it's, see, for even for 2 cross 2, it is not true. Then for any 3 by 3 or any n by n, it is not true, right? You can simply
No, I'm asking, yeah,
extend this.
these four options is not true for any order of matrix.
Yeah, so you can actually simply just add zeros
Okay, ma'am.
here to extend it to any size and argue the same thing.
Okay.
Yeah. Okay. So which of the following options are correct for a square matrix A of order n by n, where n is any natural number? So if the determinant is non-zero, so this is something which I just wrote in the previous page. If the determinant is non-zero, then the nullity of A must be 0. Is that correct?
Yes, ma'am.
In that case, this is incorrect. If the nullity of A is non-zero, then the determinant of A must be 0.
True.
Right? So nullity 0, non-zero means you
At least
have
one of
none
the
for the
row will be
element.
0.
Yeah, so in this case, you know that rank of A is strictly less than n, and hence the determinant must be 0. Okay. So what did you say at least?
One of the row will be 0.
In the RREF form, yes. If the nullity of A is non-zero, then the determinant of A may be non-zero. No, it's not possible.
False.
Yeah. Okay. If A is a 3 by 4 matrix, then which of the following options are true? Rank of A must be less than or equal to 3. Is it correct?
Yes, ma'am.
Yes.
Correct.
Yes, ma'am.
Nullity of A must be greater than or equal to 1.
Yes, ma'am.
Yes, ma'am.
Because here you have rank plus nullity is equal to what?
4.
4.
Number of column.
Columns.
Maximum possible value is 3. So it can be 3, 2, 1, or it can be 0 also, because they have not mentioned whether it is a non-zero matrix or 0 matrix. So correspondingly, the nullities are 1, 2, 3, and 4. So the nullity must be greater than or equal to 1. Okay. So this is fine. If A has two columns which are non-zero and not multiples of each other. Okay. So A is having two columns which are non-zero and not multiples of each other. Okay. So it means that these two columns are linearly
Linear combination, independent.
okay. While the remaining columns are linear combinations of these two columns. Okay. So let's say that these two columns are V1 and V2. Then you know that V1 and V2 are linearly independent, and V3 and V4, they are some linear combinations of this V1 and V2.
But there are 3 rows, ma'am. So it must be V3.
They are giving columns, not rows.
Oh, sorry, ma'am.
Okay. So these are the columns, you see that. So you see that out of the 4 columns, only 2 are linearly independent, right? So now here from this, they are saying nullity of A is 2. So from this, first of all, what can you say about the rank of A?
It is 2.
2.
2. So this first of all tells you that rank is 2. So if the rank is 2, then what can you say about nullity?
2.
2.
4 minus 2 would be 2.
Zero.
So the rank is 2, so the nullity is also 2 in this case. 2. Okay, fine. So here they are giving the same scenario, nullity is 1. So obviously this is incorrect. Okay. So this problem is fine, right? Okay. Let A be a non-zero matrix of order 3 by 1. What is the rank of the matrix A transpose?
Uh,
What is the rank of A transpose?
M
3
1
3.
plus
3.
3.
It is 3
1.
plus 3.
A full rank.
Remember, you have to use this property that rank of AB is less equal to minimum of rank of A comma rank of B. You have to use this property here. Okay. What do you, and also you have to use that. What is rank of the relation between rank of A and rank of A transpose? What do you know?
That all of its columns would be like the
Then
multiple of the first column.
rank is same, man.
1.
Rank is same.
Yeah.
Rank of A is equal to rank of A transpose, right? And in this particular scenario, you know that rank of A is less equal to 1 and it is given to be non-zero. Your rank of A is non-zero and it is less than or equal to 1 implies what is the exact rank of A,
1.
1.
right? So your rank of this matrix is exactly 1. Okay. Now from this condition, what can you say? You know that rank of A transpose is less than or equal to rank of A, because here rank of A and A transpose both are same. So the minimum is just they are same. So it is less than or equal to 1, right? So here what is the rank of A transpose then? If
1.
A is non-zero, can I say that A transpose
1
is
by
non-zero? So you can say rank of A transpose
Is 1.
is 1. Okay, fine. All right. So
Excuse me, can't we think it directly?
yeah. So how? What do you mean by directly?
It's 3 cross 1 matrix, and the transpose is going to be 1 cross 3, and simply it shows that it will be forming a matrix which is going to have single.
What is the order of AA transpose?
3 cross 3.
Okay. Yeah.
Okay. Let A be a 4 by 3 matrix and B be a 3 by 4 matrix. If the null spaces of A and B are 2 and 1 dimensional vector spaces respectively, then what is the maximum possible rank of the matrix AB? So you have A and B of these dimensions. The null space of A is and B are 2 and 1 dimension. So here we are given that nullity of A is 2 and nullity of B is 1. Okay. So here from this A is a 4 by 3 matrix. So what should be the rank of A?
1.
1.
1.
And B is a 3 cross 4 matrix. So what should be the rank of B?
2.
3.
3.
3.
3.
3.
Sorry,
Right?
3.
So now what is the maximum possible rank of AB?
1.
1.
1.
So the answer is 1. Okay, because the minimum of these two is the maximum value for rank of AB. Okay, fine. All right. Okay, moving to linear transformation, you know that this is the definition for linear transformation. And when you are verifying
Sorry,
linear
ma'am.
transformation,
Sorry,
yes.
ma'am. Last problem. Can you tell the final answer, please? Rank of.
See, here again we are using the property that rank of AB is less equal to minimum of rank of A comma rank of B. Right? Here, what is rank of A? It is 1 and rank of B is 3. So the minimum value is 1. So rank of AB is less than or equal to 1. So the maximum possible value is 1. Got it?
Yes, ma'am. Thank you, ma'am.
Okay. Okay, so when you are verifying whether a given transformation is linear or not, so this is one shortcut to see that whether it is. So this is basically sufficient, necessary condition, not a sufficient condition. So first of all, you see whether t of 0 equal to 0. If this itself is not satisfied, then you know that it is not a linear transformation, but you cannot just stop with this. Okay, if this is satisfied, then you cannot stop with this. You have to check these two conditions. Okay. Fine. So here the transformations are given. So you have to check whether these things are transformations or not. But here, I don't want to straight away look at these. Can you all tell me what is the general expression for each of these transformations? How does it look like in general?
T of
A1 is
3.
Yeah. So A, B, C, D are real numbers. Can you similarly mimic R2 to R3 in the same fashion?
AX plus 1.
Or
constant.
A2 plus
Ma'am,
B1.
it's
Why?
constant.
What is constant? What is constant?
1 here, 1.
Sorry, what?
Op-
Are you asking something? I don't understand what.
She's saying that the constant terms would be taken as it is. Like if there is x plus 1, then there would be a1x plus 1, not b1y. But it's not correct, I guess.
Are those
Why?
for the options or for the general case, ma'am?
So these are like general form I'm writing. A general form of linear transformations. Okay, now can you say what is the general form for T from? So I have given some examples here. Based on this, can you try what can be this?
AX plus B.
There is no Y. No Y here.
A mod X, comma B. B1
See, don't
Y.
compare it. See, the point I'm writing is you should not compare with
A to
specific
X.
case. No, no, no.
AX comma BX we can write.
We should
Sorry.
make two cases for this, I guess.
I can hear some answer, but can you please repeat? A?
AX comma BY.
No, there is no Y here.
I'm just write ax comma bx like new variable.
Very good. Okay, that's all. Very good. What about T from R2 to R?
And AX plus BY we can write.
Very good. Okay, so this is a general form for linear transformation. So once you know this, then whatever is given here, you can just verify. You don't have to you look for problems to understand and verify all these conditions. This is a general form. It cannot be anything different from that. Okay, so with this, can you see that whether the first option is of this form?
Yes.
Yeah. Okay. What about the option 2?
No.
It is not homogeneous.
Yeah. So this not in that form. What about option 3?
No.
No.
Ma'am, can you please give explanation about the third option?
See, here everything is of the form a1x plus b1y, a2x plus b2y. There are no constants separately. Everything is either a coefficient of x or y. It cannot be separately a constant like this. So this, any transition from R2 to R3 should be only of this form. It cannot be different from this. Okay, so here you have something different from this. So this is not possible. Okay.
The third one.
So the traditional way to do this is see the traditional way. What do? You do t of 0. For example, option 2. What is t of 0 0? So 0 0 is 1 3 1 0 and then 6, which is not 0 0 0. So you see that it is not a linear transformation. This is one way you can check that it is not a linear transformation. 8. And for option 3, this is not going to work for you. So for option 3, so either you look at this form, so it is not of this form, so you have a modulus, so it will not work, or you have the traditional way. You can check any of this condition and see that it's not going to work. For example, if you are going to look at t of -1, what is t of -1?
Minus 3 comma 0.
-3 comma 0. But t of -1 should be -1 times of t of 1. Is that correct? Yeah, it should satisfy this condition. So what is t of 1?
-3 comma 0.
It is same -3 comma 0.
But here, then what will you get? 3 comma 0. So you see they are not matching.
Yeah.
All right. See that -1 times of t comma 1, t of 1 is not same as t of -1. So it means it cannot be a linear transformation. And you see that this is of the form ax plus by, so it's a linear transformation.
But in third option, t of 0, it won't be 0 comma 0, ma'am.
T of 0 is also 0 comma 0 only. What's wrong with that?
No, so that satisfies that.
That's why I told you in the very beginning, this is only a necessary condition, not a sufficient condition. Okay. All right. So is this problem fine for everyone? Shall we move on? I guess with this idea, you will be able to verify any such question. You can be able to handle any such question. Okay. Fine. Okay. So, okay, before answering this question, let me just ask you two things. What do you know about range of a linear transformation? It is a subspace of
codomain.
So it is T from R2 to R2. So specifically, it is a subspace of
R2.
What are all the possible subspaces of R2?
So, ma'am, a point,
A straight
a
line, a
straight line,
point,
or
and a
two
plane.
entire.
Okay, so these are the possible cases. Now we can easily answer this question. There exists a linear transformation T from R2 to R2 whose range is contained in the circle x squared plus y squared equal to 1. So first of all, your range should always contain the zero vector. So now this set, does it contain the zero vector? So suppose x comma
No.
y is 0 squared plus 0 squared is 0, not equal to 1. So this does not belong to the circle. So this, if does not belong to this, then this cannot be containing your range because range contains 0. So option 1 is not possible. Is that clear? Yeah. Okay. What about option 2? You tell me the answer. Option 2.
Correct.
Yes, it's correct.
Yes, ma'am,
Okay.
it's possible.
Okay. What's such a transformation? Can you say?
A point or a line.
What is exactly T of x comma y in this case?
Line passing through origin.
Ma'am, it doesn't contain the origin.
My
Zero
question
vector.
is, what is exactly T of x comma y?
It is a line.
X,
Ma'am, XX.
comma X.
Okay.
Either X or either Y, both
Yeah,
can't.
any of them can satisfy this. So T of x comma y is x comma x. If you take this case, so in this case, your range is this straight line. So the set of all x is equal to y in the sense that uh, x in R, right? So it is span of 1, 1. Okay. What about this one? Again, what about 0, 0? Does 0, 0 belongs to S?
No, ma'am.
No, it does not belong to S. So this case is not possible. So second option is possible, third is not possible. What about option 4?
Ma'am, why option third? I just
Yes,
missed
ma'am.
that. Option third.
Origin should be in range. Here they are saying range is in S, but this S is not having the origin.
Okay, ma'am.
What about option 4?
Yes, ma'am. It could be true.
Yeah, so in that case, what is your T of x comma y exactly? Can you say?
Ma'am, x comma pi x.
Pi x.
Okay, so this is possible. Okay, fine. So remember, line through origin means what is the equation it will have? Y is equal to mx. Okay, so that's why y equal to any m, you can take here m is 1. Okay, fine. Okay, so the next thing, we are moving to a linear transformation T from V to W, where V and W are vector spaces, is called a monomorphism. That is an injective map. So T of V1 equal to T of V2 implies V1 equal to V2. So this is the definition of injective map. And epimorphism, that is a surjective map. If so, in short, you can say that in this case, range of T is your entire W. And in this case, you see that kernel of T is, can you say, for injective map, your kernel is
0.
0.
0. Okay. So isomorphism means both these conditions are true. Okay. So remember, 1 to 1 means you know that kernel is 0. So this means that your nullity is
0.
0. Okay. And on to means you know that range is W, and in that case, rank is dimension of W. Okay, and isomorphism. Isomorphism means you have both these conditions. So if both these conditions are there, then what will you get? You have nullity is 0. Your rank of T equal to dimension of W. So what is your rank nullity theorem saying? Rank of T plus nullity of T equal to dimension of
W.
both these are applying here, then you will get dimension of W plus 0 equal to dimension of V. So what is that you are getting for isomorphism? Isomorphism means you will have dimension of V equal to dimension of W. Okay, so these are the important things you should know about one-to-one and isomorphism. Okay, good. Now with this, can we quickly answer these questions? T is a one-to-one linear transformation if and only if there does not exist any V non-zero such that TV equal to 0. So this means that if there is no V non-zero such that TV equal to 0, so this statement exactly says that your kernel is not
Kernel is
0,
0.
0, right? This means this, right? So this means this option is correct, right? This is what we saw.
Now,
Yeah?
how kernel is 0 in this case?
Because there is no non-zero vectors in kernel. That's what they are saying, right? Kernel is set of all v such that tv equal to 0. And in that set, they are saying there is no non-zero vectors.
Okay, fine, ma'am. Thank you.
Question 2. If T is surjective, then it cannot be injective. Is that true?
No, ma'am, wrong.
Wrong, right? We have transformations which are both surjective and injective, right? Okay. So we have both surjective and injective maps. So this is obviously incorrect. What about option 3? If T is from R to R is a linear transformation which is not injective, then T must be 0. What do you say?
No, ma'am, wrong.
Not true.
No, no.
Okay, so first of all, T is from R to R is a linear transformation which is not injective. So what does it say? If it is not injective, what do you know? You know that kernel of T is
Not 0.
not 0. So you have some non-zero vector. So V not equal to 0, V belongs to kernel T. Right? So now you have TV equal to 0 for some V non-zero. And you have R, okay, R. And V is in kernel. And what is the dimension of kernel now? Because it has a non-zero vector. What is the dimension of kernel? What is your dimension of kernel, let's say? Yeah, what is the dimension of
One.
kernel? Yeah, 1. Okay, so this means can we say that your kernel is actually your entire R? Because kernel T is a subspace of R and its dimension is 1. So this implies kernel T is equal to R. Is that correct? Yeah? Yes or no? Why there is a complete silence? Did I say?
Ma'am, can you explain this once more?
See, kernel T is a subspace of R. Do you agree with that?
Yes, ma'am.
Okay. And you see, since we have a non-zero vector in the kernel, the dimension of kernel is 1. It cannot be beyond 1, right? So it should be exactly equal to 1. So if you have a subspace which is having the same dimension of the original space, then the subspace should be equal to the space.
Yes, ma'am.
Okay. So if the kernel is the entire space, then the transformation is a zero transformation, right?
Yes, ma'am.
So is this true or not?
It's true, ma'am.
Yeah.
Ma'am,
So, ma'am, only because it's R to R, we can infer that it's a zero
Exactly.
transformation.
Because it is from R to R. Yes.
Yes, ma'am.
Okay. So this
ma'am,
option.
if dimension of kernel is same is R, kernel is R, then how come this TV is equal to 0?
See, your kernel is the set of all V such that TV equal to 0. And that is your entire domain. So it means all vectors here are going to 0.
Yeah.
Got it?
All vectors are going to 0.
Yeah.
Can you elaborate, ma'am? I didn't still.
See, kernel is the set of all V such that TV equal to 0. And this kernel is your domain. So this means what? All elements in your domain are going to 0.
Yes.
Right?
Yeah.
So that is what is written here. TV equal to 0 for all B in R. Okay?
Yeah.
If there exists a non-zero vector V in V such that T be equal to 0 for a linear transformation T from V to W, then T cannot be an isomorphism. So
Yes, ma'am. True.
non-zero, yeah. So this first of all means that your kernel is non-zero. If kernel is non-zero, you know that T is not one-to-one and hence it cannot be an isomorphism. Right? This is true. Is this clear?
Yes, ma'am.
All right. Okay. If T from R2 to R2 is a linear transformation such that T of x comma y is x comma 0, then which of the following options are?
I'm only on to.
T is not 1 1 but on 2.
Option 4.
Yes, ma'am, it should be neither one.
Option 3.
Option 4. Ma'am, option 4.
Option 4.
Okay. See, listen to this. Look at this statement carefully. Whenever you have the domain and codomain same, then T can be 1 to 1 if and only if it is on 2. It cannot be just 1 to 1. And okay, so here, did I make anything wrong? Okay. Implies, yeah, it is correct only. T is 1 to 1 if and only if T is on. It's correct only. So in this case, you see that, see, either you can use this statement and directly say that if it is 1 to 1 and check whether you can say, definitely you can say that it is 1 to 1 but not on to is incorrect. It is on to but not 1 to 1 is incorrect. You can say this from the statement. But whether it is both 1 to 1 on to or neither 1 to 1 and on to, that is what is the only thing. Okay. So here you see that T of x comma y equal to x comma 0. So what is the matrix representation? 1 0 0 0. Yeah. Yes or no?
Yes. Yes, ma'am.
So rank of A is 1. Nullity of A is 1. So this means this is not on to, not 1 to 1. Okay. So neither 1 to 1 nor on to. Is this clear?
No, ma'am.
No,
Why not
ma'am.
on 2?
Okay. See, here if T is 1 to 1. What do you know? If T is 1 to 1, nullity is 0. Yeah. If nullity is 0, you know that rank of T is equal to what? According to rank nullity,
Dimension.
dimension of V. If rank of T equal to dimension of V, in this case, domain and codomain are same, and hence this means that T is onto. Okay, so you exactly go back in the same order, you will get this. Okay, because the domain and codomain are same in this case. So here, either you look at this and first of all, you can say that option 2 and 3 are not possible. Because if 1 to 1 is there, then on to should be there. And if on to is there, 1 to 1 should also be there. So either option 1 or option 4 is possible. So in this case, you see that obviously this is a matrix of rank 1. If it is rank 1, so you see that this condition is not satisfied. So it cannot be on to. Similarly, if nullity is 1, then it cannot be 1 to 1. So it is neither 1 to 1 nor on to. Is that clear?
Ma'am, if rank is 1, then how it is not on 2?
Okay, if rank is 1, then what is your range? Can your range be entire R2?
No.
No, ma'am.
So if it is not entire R2, can it be onto?
No, ma'am.
No. Okay.
Okay, fine.
Yeah, ma'am.
Right. So I hope this problem is clear for everyone. Shall we move on? Yeah.
Yes, ma'am.
Okay. So next we are looking at matrix representation. You know how matrix representations work, right? So here, this is the problem, similar problem you are having here. So only thing here, you have a different transformation. Again, use the matrix representation. What is the matrix representation of this? What is T of 1, 0?
1, 1, 1 minus 1.
1 minus 1.
T of 0, 1, 1 minus 1. Right? Now, is this matrix invertible?
Yes, ma'am, it is.
So you know that rank of A is 2. So you know that T is on 2. If T is on 2, you know that T is 1 to 1, because T is from R2 to R2. So it is both 1 to 1 and on 2. Is it clear?
Yes, ma'am.
So since T is on 2 and the domain and codomain are same, it is also 1 to 1. Okay, fine. All right. So, okay. So T from R2 to R2 be a linear transformation such that T of 2 comma 1 is this and T of 1 comma 3 is this. Which of the following options are true? Okay. So either you can simply plug in this 2, 1, 1, 3 and see whether it satisfies or not. But I would like to tell you what is the way to find exact T of x comma y, because everyone can easily check whether 2, 1 is satisfying this or not, 1, 3 is satisfying this or not. It is better if you know how to exactly compute T of x comma y. How to compute T of x comma y? So for computing x comma y, so first of all, 2, 1 and 1, 3, are they linearly independent?
Yes, ma'am.
Yes, ma'am.
If they are linearly independent, can we say that this forms a basis for R2?
Yes, ma'am.
If it
Yes,
forms for R2, can I write any x comma y as a linear combination of 2 comma 1 and 1 comma 3?
yes, ma'am.
Yes, ma'am.
So in that case, can I write x is equal to 2 alpha plus beta and y is equal to alpha plus 3 beta? Yes or no?
Yes, ma'am.
Yes, ma'am.
Now if I solve this equation, so let's multiply equation 2 with 2 and I have equation 1 as it is. So you have 2 alpha plus beta equal to x, and then you have 2 alpha plus 6 beta is equal to 2y. So if you do some simplification, you will get minus 5 beta is equal to x minus 2y. So your beta is minus 1 by 5 x minus 2y. Now can you find what is your alpha from this? Your alpha is y minus or plus 3 by 5 x minus 2y. Is that correct? I have just substituted the beta value here. Okay. So what will you get? 3 by 5x. Can you simplify quickly and tell me? Total silence. Just simplify this
1
and
by 5y.
sorry?
Minus 1 by 5.
Minus 1 by 5.
Minus 1 by 5, 3 by 5. What's the answer? So here you have minus 6 and here you have 5. So minus 1 by 5, right? Minus 1 by 5 times of y. So you have got your alpha and beta, right? So if you have got your alpha and beta, now what is the next step? So now you have to simply find T of x comma y is alpha times of T of 2 comma 1 plus beta times of T of 1 comma 3. Do you know the values of T of 2 comma 1 and T of 1 comma 3?
Yes, ma'am.
So it is 3 comma 2 and 0 0. So it is alpha times of 3 comma 2 plus beta times of 0 0. So here, what is your alpha is 3 by 5x minus 1 by 5y times of 3 comma 2. So when you just multiply, you will get, maybe let's put 1 by 5 outside. So you will have 9x minus 3y comma 6x minus 2y. Does it match with any of your options? Yeah, option 3. Okay. So,
Ma'am, I have a doubt, ma'am.
yes.
Suppose this 2 comma 1 and 1 comma 3 aren't linearly independent or
Mhm.
something, then how do we proceed?
If it is not linear, if it is not linearly independent, usually you will not be able to determine the transformation.
So in the exam, it would be given as a linear independent basis, right?
Then this option is there. Remember, this option is there. Option 4 is there. If they are not linearly independent, then you have this option. T cannot be determined from the given information.
Okay.
Okay?
Also, ma'am, because the given domain is R2, so there has to be two elements in base for basis. So with one element, we cannot determine if.
Yes, with one element from the basis, you cannot determine. Right? And also with one element, you can first of all say whether it is a linear transformation or not, right? Because it should satisfy the linear transformation property. That you can at least check. It depends on the problem.
Yes, ma'am.
Okay, fine. Okay, so everyone, attention, because we are kind of summarizing the things we have seen so far in week 5. Okay, so T from R3 to R3 is a linear transformation. We have some transformation. Don't worry about this A1, B1. They are some numbers, some real numbers. Okay. Now, T is injective if and only if the system of linear equation AV equal to 0 has a unique solution. So if the system of linear equation having a unique solution is same as null space of A equal to
0.
0.
0. So if null space of A is 0, you know that T is
Injective.
injective, right? And if null space of A is 0, you know that nullity is 0. You know that nullity is 0 means rank A is 3, right? So this implies nullity is 0. So nullity is 0 implies rank is 3 because you have 3 to 3, right? And if the system of linear equation AB equal to B for any B in R3 has a solution, for any B in R3 has a solution. What does this mean? So for
Every element of codomain has a pre-image.
exactly, for every element in codomain. So this is an element in codomain. So for every element in codomain, so this V is your pre-image. Okay, so you have a pre-image. So it means that it is one. So this is exactly the definition of surjective. So for every element in codomain, if you have a pre-image, then you know that it is surjective. So this is the definition of surjective. So it's fine. Okay, if T is not surjective, okay, then there exists some B in R3 such that AVB equal to has no solution. So this here means that, so for some element B in codomain, there is no pre-image. This is exactly when we say that it is not surjective. So again, this is correct. So basically, I don't know. So the same thing you are just flipping this way, that way, and testing whether you are really understanding it or not. That's all. So here, all these options are twisting the same thing this way and that way, and nothing new is done in this. But anyway, you see that you just have to understand what is given here. Just twisted this way and that way. Okay. Is that clear? All these options? Yeah.
Yes, yes.
Finally, after 1.5 hours, we are moving to week 6. Okay, fine. Okay, so we know that null space is a surjective. space is nullity, dimension of range is rank, and T is injective if and only if kernel is 0, and T is surjective if and only if image of T, which is nothing but range of T, both are same, is W, and T is injective if and only if nullity is 0, and T is surjective if and only if rank of T is dimension of V. All these things I have already covered. And two spaces of isomorphic if and only if there exists an isomorphism between T from V to W. Okay. And any n-dimensional vectors, this is an important thing. Any n-dimensional vector space is isomorphic to Rn. Okay. So in fact, a more general statement here is that, so any two vector spaces of same dimension are isomorphic. Okay. I don't know. I have given some proof of this in some of my live sessions. If you want, you can go back and check. Okay. So consider a map T from R2 to R2 defined as T of V equal to AV. So your V is x comma y, A is 1, 2, 2, 1. So which of the following options are true? See, forget about these numbers 1, 2, 2, 1. Okay. So you know how to obtain a matrix from a linear transformation. How to obtain a transformation from a matrix?
We just multiply it by whatever one, how many the variable is, like a into v x y for 2 cross 2 matrix.
Exactly. So it, for example, suppose you are having, let's say R into Rm. Okay. So first of all, let's say you have an m by n matrix. Okay. And you take any V in Rn. Okay. So TV equal to AV defines a linear map T from Rn to Rn. Okay. So this, if you know, then you don't have to worry about what are the entries of the matrix. That's all. It always defines a linear map. So in that case, you know that this is going to define a linear transformation. Is that fine? So the first option is obviously true. Okay, you don't have to verify anything. This is always true. Okay, whether they are one-to-one or on-to, that is something you need to verify. But you know that it cannot be either one-to-one or on-to alone. Either it has to be both or none. So option 4 is obviously incorrect.
Well, both.
Dimensions are same. So now what is the determinant? The determinant here is non-zero. So they are both one-to-one and on-to. Okay.
Ma'am, can you please down the screen just once? Yes,
Okay.
ma'am. This fact. Can you please just elaborate once again? I didn't focus on that point, the last point. Yes, ma'am.
So any two vector spaces of same dimensions are isomorphic. So I don't know whether I have a question of that sort. Yes, I have included a question where that I just
Ma'am,
now,
excuse me.
hold on, hold on. Let me first complete answering her. Mm, no, I don't have. So let me quickly answer this question and then I will come to the other question. One
Okay, ma'am.
Yeah. So let's say that you have something like this said x comma y, x plus y is equal to 0. Now this is a subspace of R2, right? What is the dimension of S? Can you quickly say?
Ma'am, 1.
Now let's say S1. Now S2 is set of all x comma y, 0 x 0 0. Let's say x in R. This is a subspace of subspace of R3, correct? What
Yes,
is
ma'am.
dimension of S2?
1.
1.
But S1 and S2 are isomorphic because of the condition which I have mentioned here. Any two vector spaces of same dimension are isomorphic. Okay, so you can do it for any dimension. For example, if you take W1 is equal to maybe, let's say, just R2 itself, entire R2. Okay, and W2 is simply the XY plane in R3. Okay, you know that W1 dimension and W2 dimension both are equal to equal
2.
to, yeah, and hence W1 is isomorphic to W2. They are isomorphic. Okay, so this is what this statement tells. Any two vector spaces of same dimension are isomorphic. Clear? Okay, so what was the other question someone was asking and I stopped you? Sorry.
Then isomorphic, if two vector spaces are isomorphic, that means a linear transformation can be defined onto
Exactly.
surjective linear transformation can be defined.
One to one and on to. Yes,
Onto
both.
one.
Yeah. Okay. Fine. Now consider the following set S. This is set of all x comma y such that x plus y is equal to 1. So in column A, you have the matrix representation of some linear transformation. Okay, in column B, you have T of S. So, and in column C, you have the geometric representations. Now you have to match them up for this S. So your S is x plus y equal to 1. Set of all x comma y such that x plus y is equal to 1. Okay. So how do you calculate this? So you have this matrix 1 minus 1 minus 1. Right. So first of all, x plus, maybe I'll write it here. This means that your y is equal to 1 minus x. So you are going to simply check what happens to x comma 1 minus x. So what will happen here? Can you calculate quickly? X minus 1
Plus x.
and here minus x plus 1
Minus
minus.
x.
So you will have 2x
X minus 1.
and
2x plus 1.
1 minus 2x. Right? So this is what you are having here. So the negative, so one is the negative of the other. That's all you are having. So here you see that y is equal to minus x. So does this satisfy this relation?
Yes, ma'am.
Okay, so you see that this is the image. Okay, so here that s is always the same, only your t of s is and y is equal to minus x. Okay, so y is equal to minus x, which is y is equal to minus x. It is a line passing through origin. So this is the option matching with it. So the same thing we can try here. 1 minus 1, 1, 0. What happens to x 1 minus x? What happens here? X plus 1 minus x, simply minus x. So you are having 1.
Ma'am, why you are multiplying with the x 1 minus x?
Because you are looking at what is t of s. And your s is, okay, s is set of all x comma 1 minus x. So I want to see what is t of s. So I'm taking an element of this and putting t of.
Okay, ma'am. I didn't see the questions condition. Sorry.
Okay. So I skipped this one and okay, let me maybe first complete this. So here the first entry is always 1 and the second entry is minus x. So here which option will match? So first entry is always 1. So this is the one which you have here. Okay, and second entry is something. So this is the one you have, x comma y is equal to 1. Okay.
Option 1 is the third column.
So for this 3, it is E. And you see that x is equal to 1 means this is the one, right? Yeah.
But there 1 and minus x, right? Here we have 1 comma y positive. No need to check for negative value.
No, see here, the only thing we are concerned is that your first coordinate is always 1. That is the only condition you are checking. Because when you are varying your x, so x is any real number, right?
Yes, ma'am.
So here you will get all possible real numbers here.
Okay. For negative value also, if we put
Yeah.
negative minus 1, it will be 1.
Yeah.
But if we take positive value, it will be minus 1 only, right? So 1 and minus 1.
Yeah, so all values you will get anyway. So it means you are getting all possible pairs of 1 comma any real number. That's why only this condition. Got it?
But here it is only positive value only, no, ma'am. Second one. Y is positive only right here.
No, y is above and below the blue line. Y is positive as well as
No,
negative.
geometric, okay, in second column.
Y is just all real numbers. It's not mentioned as positive.
Okay. Sorry. I just.
Also, ma'am, if we look at the member of S, minus x equal to y plus 1 as given above in the formula.
Where?
In the very first line in the question itself.
Yeah.
More above, sir, ma'am. More, yeah. It's written s equal to, I mean, in the set S, y equal to 1 minus x. That means if minus x equal to y plus 1, y minus 1.
Yeah.
Okay,
Minus x is equal to y minus 1. What you get from that?
No, nothing, ma'am. I was trying to find if y it is has to be y always.
Okay.
It's fine, ma'am. Understood.
Okay. So here in this case, then what is happening? So you have x 1 minus x. So you will have minus 1 plus x. And then here you are having x plus 1. And then, oh, x minus 1 plus x. Right? So you are having minus 1 plus x and then minus 1 plus 2x. So here, what's happening here? 2x minus y is equal to minus 1. Is that correct? So what is 2 times of minus 1 plus x? Minus 2 plus 2x.
Yes.
And then you put minus 1 minus 2x. So you have plus 1 minus 2x, which will give you minus 1. So 2x plus y, you will get minus 1. Okay, so this is satisfying this, and 2x is equal to minus 1. So yeah, this line you can see. Okay, you can plot some points and check that it is going to look like this. Okay, and in fact, it also crosses yes. Okay, at some point. Okay, so this is how you have to deal with such a problem. I guess you have an idea to solve such problems now, I guess.
Yes,
Okay. Okay, good. Okay, so if the matrix of the linear transformation with respect to standard basis is this, which of the following is an appropriate definition? This is very easy because we have done something difficult where the basis is not standard basis. Now it's just standard basis, so the problem is much simpler. So you know what is TE1, you know what is TE2. What is T of x comma y then? X TE1 plus y TE2. Yeah, this is what we did here also, right? Where was that? Here. X comma y, first we need to write it as vectors. So here x comma y, if you express it as a linear combination of the basis vectors, it is simply x e1 and y e2. Then apply the linear transformation. So what is T1 from this transformation, from this matrix? What is T1?
2
2 comma 1.
And what is T2?
3 comma 4.
So it should be 2x plus 3y and x plus 4y. Correct? Okay.
Yes, yes.
So If given if it is given that it is standard basis, either you can do this, or the other thing you can do is that you can simply find AXY. You will still get the same thing. Okay. So you can try that also. So 2x plus 3y, x plus 4y. This is the answer. Okay. So you can check that it will be same as this. Only for standard ordered basis, you can do this. If it is something else, you cannot do this. Okay. Fine. Okay. Now for this above transformation, which of these following options are correct? So T is 1 to 1, T is on to, so which one? So look at the matrix. What's the determinant? 8 minus 3.
Non-zero.
It's non-zero, it should be an
1 and on to.
Isomorphism.
Isomorphism.
Okay, fine. Now suppose the matrix of a linear transformation T from R3 to R3 with respect to this ordered basis and some other basis is I3. So you have the identity matrix represented with these transformation, with these bases. Now, what is your matrix A? What is the determinant of A they are asking? Okay, so how do you find the determinant? Okay, so how many of you remember what we have seen? Okay, for similar matrices, you need the same transformation. So that is quite something different. We cannot use similar matrices. I thought we can use similar matrices. Okay, though in that case, so how do you go about this? Can anyone say how to
At
do
first,
this?
at first we have to find the transformation matrix. Then we can go for it.
Exactly. So here, let's say suppose this is your V1, V2, V3, and this is your W1, W2, W3, right? So your TV1 is E1. Okay. So TV1 is not E1 exactly. So it's 1W1 plus 0W2 plus 0W3, because that is your first column, right, of
Yes,
identity.
ma'am.
And TV2 is 0W1 plus 1W2 plus 0W3. And TV3 is 0W1 plus 0W2 plus W3. Right? So this is what we have. Right? So from this, can we find what is T? So this is V1 is same as E1. Right? So you know what is TE1 already. TE1, what is TE1? 111.
111.
Okay. Now, how to write E2 in terms of this V1, V2, V3? I want 0, 1, 0. Can I write it as V2 minus V1? Yeah. So, TE2 is simply TV2 minus TV1. So, what is TV2 minus TV1? 0, 1, 1 minus 1, 1, 1. Correct? Yes or no?
Ma'am, can you explain again this? I have not got.
Which part? Did you understand the first step?
First step, why you are expressing V1 in terms of W1, W2, W3?
Because that is what is given. See, they are writing that. So when beta is the domain and gamma is the basis considered for codomain, the matrix you are getting is the identity matrix. So T beta gamma is 1 0 0 0 1 0 0 0 1. Okay. So you are expressing TV1 in terms of the elements of W1, W2, W3. So 1
And
W.
if the transformation is identity matrix, then it should not change the identity of the basis.
See, you get the identity transformation only with respect to this basis. That's why I have written it in this way.
Okay.
Okay.
With respect to the one, that means 100 become 100 only.
Sorry, what?
In beta 100 vector, it becomes by this identity transformation, it remains 100 only.
With respect to this basis. But actually it is mapped to, you see TV1 is 1 W1. The other things are 0. So actually TV1, T of 100 is 111.
Ma'am, but it is an identity transformation, so it should not change.
It's an identity transformation with respect to this basis, not for with respect to standard order basis.
Okay.
Okay.
A little bit, yeah.
Okay. Now you see that E2, which is 0, 1, 0, is nothing but V2 minus V1. So you apply the transformation and you get that TE2 is minus 1, 0, 0. Okay. Is this fine? And what is TE3? How to find E3 first of all? Can you quickly say? E3, how do you write it as a linear combination of V1, V2, V3? Yes, Bhumi?
Ma'am, could you please tell the E2 part once again?
This one.
E2 equals to V2 minus V1. Actually, I don't understand that part.
What did you not understand? E2 is 0, 1, 0. So 110 minus 100 gives you 0, 1, 0. What's
Yeah, ma'am, got it.
okay? So same way, how can we get E3? Can someone quickly say that?
Ma'am, V3 minus V2.
E3 minus V2. So
V3
what is,
minus
yeah, so what is TE3 in that case?
Ma'am, W3.
So TV3 minus TV2. So you see that TV3 is actually 0, 0, 1 and TV2 is 0, 1, 1. So you will get 0 minus 1, 0. What is your matrix A then?
Ma'am,
1 1 1 minus 1 0 0 0 minus 1 0.
Okay. So what's the determinant of A?
TV3 minus TV2.
1. Right? So the answer is 1. Okay.
Ma'am, just by chance, is there any relation between the determinant that we got in the earlier matrix and this matrix? Because earlier
one
also,
and what?
In the other basis, the given basis, it's given that it's the identity matrix. So also determinant will be 1.
No, so we can say that there is a relation if both these bases are same. But since the bases are different, we cannot say that.
Yes, ma'am. Okay.
Okay.
Ma'am,
Yes.
if we want to get general representation of this problem in the form of x, y, z, then how would we get?
Then it's very easy. You have already got what is your A. So once you know what is your A, E of x comma y comma z is A of x y z. You simply have to multiply x y z with A and you will get the answer. Okay.
Okay, ma'am. There was a condition for this, means sometimes we cannot multiply directly.
Yeah, so if A is a matrix with respect to the standard ordered basis, then this is applicable. Here A is with respect to standard ordered basis and hence this we can do.
Okay, ma'am.
Fine? All right.
Yes, ma'am.
Okay. So this is something I have already explained. T is injective means you have this and T is isomorphism means you have the dimensions to be same. This comes because of the rank-nullity theorem. Okay, so let me quickly see how many problems are there. I guess there are 3 more problems. I'll try to tell what is the logic of this. Okay, so in the first case here you are having a transfer. Please mute. There is too much background noise. Yes. Consider the following linear transformation T from R3 to R2. T of x comma y comma z is 2 x plus 3z, comma 4y plus z. So you need to find the null space, find the dimension of the null space, and then check whether it is an isomorphism or not. So finding null space and dimension, do you think you need my help to do that? I guess these two part are quite easy for you to do, I guess. Can you manage on it on your own, these two
Yes,
things?
ma'am.
Ma'am, we're
Okay.
supposed to extract the matrix, and then we have to suppose, and then we should find like the null space, right?
Exactly, that's all.
Okay.
Okay, so you just have to write what is your matrix. So you have to first write T1, T2, T3, and then you are done. So here you will get 2 E1, right? So for E1, you
Zero
will
and
get 203 and
no, ma'am. 203 in
Ma'am,
column.
it's 2 by 3 matrix, no?
yeah, so you will get 2 and then you will simply get here it
Ma'am,
is
zero.
0. Okay, and then here you are getting
Zero.
TE1, TE2 means 0, 1, 0, so you have 0 and 4, and TE3 means you have
3 and 1.
and 1. So this is the matrix you have. For this matrix, you have to find the null space and find the dimension of the this is the range. So you are this is basically asking the rank. So first is the null space and second they are asking the rank. What is the rank? Can you immediately answer from looking
2,
at the matrix
2,
by
2.
looking at 2. So the rank is
So,
so if the rank is 2, what can you say about so this null space? Yes, you need some calculation. But with rank, when rank is 2 and you have t from R3 to R2, okay. Now what can you say from this? If rank is 2, what do you say about nullity?
Zero.
Nullity exists.
1.
Nullity is 1. 2
Zero.
plus is 2.
0,
So
0,
what?
0.
0, right? So if nullity is 0, you know it is 1 to 1. If rank is 2, then what?
On to.
On 2. Okay.
Excuse me, ma'am.
There is
So
no.
T is
It cannot be both 1 to 1 and on 2. If it is both 1 to 1
Ma'am,
on 2,
nullity
then
is 1, no?
And
Ma'am,
the
nullity is
matrix
1,
is
it is not 1, 1.
2 plus 1 equals to
yeah,
3 should be, na?
yeah. Correct, correct. Here it is 3, right? Yeah, that's what I was wondering. Here it cannot be both 1 to 1 and on 2. Yeah. So here nullity is 1, so it is not 1 to 1.
Only 1, 2.
Yeah. So sorry. So
Ma'am,
nullity
excuse me.
yes.
Ma'am, just one thing. If the dimension of the subspace image T is defined as rank, can you tell about the nullity? I forgot definition in this way.
From rank nullity only I can say. So if you know the rank, yeah, because of this condition here. So I'm using rank to the nullity here.
No, no,
Okay.
ma'am. The definition of nullity, the way rank given a dimension of subspace. In this way, nullity definition.
Nullity is dimension. Fine.
Okay, ma'am. Thank you.
Okay. All right. So you know that in this case it is on to but not 1 to 1. On to but not 1 to 1. Okay. Fine. So consider a linear transformation T from R3 to R3 defined in this way. Okay. So what is the matrix representation for this? So T of 1 0 0 is 1 minus 1 0. T of 0 1 0 is 1 0 1. T of 0 0 1 is 0 1 1. So you see that this is the matrix. So option 2 is correct. Okay. And basis for the range is given as the standard basis. So what is the determinant of this matrix? Let's call this A. What's the determinant? Is it non-zero?
Yes, ma'am.
Zero.
If it's non-zero, you know that the range is entire R3. So if range is entire R3, then this is a basis for the range, right? Yeah, because this is a basis for the
I
R.
think the determinant is
The
zero.
determinant is 0, by the way.
Okay, so let's check. So 1 times of 0 minus 1, and then minus 1 time of minus 1. So you will get minus 1 and then plus 1. Yeah, it's actually 0. So 1 minus 1 0, 1 0 1 0 1 1. Yeah. In this case, the range cannot be R3, right? So now you have to check whether this forms a basis for the range. So do you observe any, so here you look at the column space. So here it is given as 1 1 0 and 0 1 1. So 0 1 1 is one of the columns. Can you get 1 1 0 from this? Can you get 1 1 0 by making any linear combinations of these columns?
Ma'am,
110 is the first row itself.
R3 minus R2.
R3 minus R2.
We get
Okay, you are looking at row, or can you look at the column? Because you are looking at the range of T. Look at the columns and tell me.
No, ma'am.
Does this belong to?
Ma'am, C2 minus C2 minus C1 gives C3.
C2 minus C1 is 0, 1 and 1. Yeah, so you see that C3 is C2 minus C1. So you can say that the rank is 2. But whether 110 belongs to the range or not, that is what you need to check. 110 is the range. So for that, maybe you can take any two columns and try to see whether you are able to write it as a linear combination. For example, maybe you can choose this two or this two, any two columns you can choose, any two linearly independent columns, right? So alpha times of 1 minus 1 0 plus beta times of 1 0 1. So if you do that, then you will get that. So alpha plus beta is equal to 1, and you have minus alpha 1 is equal to minus alpha, and what is your beta in that case? Beta is 0. So alpha is equal to minus 1. So this is not possible, right? Beta is 0 and alpha is minus 1 cannot give. So this is not possible. So this means this vector does not belong to the range. Please mute. Please mute. So this means this vector does not belong to range. Okay, do you see why? Because it is not expressed as a linear combination of the basis of the range. So this does not belong to range. So this also does not form a basis. Okay, and the rank of T is 2, right? Rank of T is 2, and if rank is 2, you know that nullity is 1. Okay, are we done? Okay, so then only one last problem is there, I guess. Oh, this looks like very much the previous problem, so I guess you can deal with this one as well. I try to cover as much as possible in week 6, 5 and 6, and I hope that this will be useful for your exam. Okay, so you have another TA session on Saturday. So whatever doubts are still remaining, please hold it for the TA session because we are already late. Any questions from particularly maybe the topics which we covered today, not any specific problems?
Ma'am, I have not understood problem number 19 actually.
This one.
No, ma'am. Yes, ma'am. This one.
See, which part you don't understand? Tell me that first.
Ma'am, first the procedure itself, ma'am. This TB1 is equal to W1. Why you are expressing in terms of
You
this?
don't understand this. This means that you don't understand matrix representation properly. What is matrix representation, first of all? So this is the matrix representation. Sorry, where was it? Somewhere I have given the entire definition. Where was it? Yes, here I guess. So, yeah. So if you have a basis T V1, V2, Vn, and then you have some other basis W1, W2, Wn, and you are able to write it in this way, then the matrix is A11, A12, A1n, and so on. Now you are given V1, V2, V3, and then you are given W1, W2, W3. Okay, and then you are saying that this matrix is your identity matrix. So what I did, I just wrote it in this format. From this information, I wrote it in this format. If I write it in this format, I will get TV1 equal to 1W1 plus 0W2 plus 0W3. And TV2 is 0W1 plus 1W2 plus 0W3. And so on. You understand now?
Yeah, ma'am.
Okay, so this is the basic concept of what is meant by matrix representation. Okay. Now from this onwards, I guess they are pretty direct. So you are just putting some values from here and there. So T of V1 is W1. So from this you are computing what is T of E1. So as usual we did in these previous cases like here. Okay.
Yeah.
All
Yes.
Ma'am, can you, I mean, if there are more pages left in your
Yeah.
PDF, can you just scroll so that it will come in the video and we can refer it later?
Anyway, I'm going to put this PDF in your notes, so don't worry about it. Okay.
Okay.
Okay,
Ma'am,
this is
because finding the previous days sessions are getting very difficult.
why?
Ma'am, also in the that list where we data sheet where we maintain TA sessions, we are not getting all the session details there.
TA sessions I will check, but the live session notes, I guess that they are very clean. I have checked it several
Yes,
times.
ma'am. Yes, ma'am. Instructor session is no problem, but TA session is. And also, ma'am, in that that sheet, ma'am, TA session earlier we were recording with the week wise, like week number was there, but now week numbers are not there, so we have to, make a
Okay.
guess based on date, which week it could be, and then
Okay,
we.
that I will see whether I can do anything regarding the TA session things. Okay.
Okay, ma'am. Thank you, ma'am.
All right. So I'm uploading this week 5 and 6 notes.
Ma'am, I have one more doubt, ma'am.
Yes.
Ma'am, I actually came across a few problems where they just gave us some t with some vector in the domain space. I'm just wondering that, and based on this, they asked us to find, the like some equation for a t of x comma y something, ma'am.
Exactly. That is what I explained today, right?
Yes, ma'am. Actually, for independent variables, I'm just asking, like, will they give us some dependent variables or something? I was confused, in that.
See,
Like,
you so far all the questions which are there existing in that model, they are usually linearly independent. If they are dependent, then I already told, then you cannot determine T from the given information.
okay, ma'am. Okay, ma'am. Thank you.
Okay, fine. All right, then wish you all the best for your quiz too, and I'll see you all after your quiz too. Okay.
Okay, ma'am.
And from where should we collect the video?
As usual, in your YouTube playlist, go and check there.
Then for session 7 and 8 also tomorrow is the session, na?
Tomorrow, yes, you have another revision session for weeks 7 and 8.
You will not be handling, ma'am, tomorrow?
No.
Okay.
All right. Okay. See you all. Bye bye.
Thank you, ma'am.
Thank you, ma'am.